The following program is brought to you by Caltech.
So I'm taking over Hiroshi's role. I'm not as fast as he is, so the question period will be a little longer. Our first speaker for the afternoon session is Wayne Hu from University of Chicago, and the title of his talk is, sign of my age, Creative Tension Between the Early and Late Universe.
Thank you for the opportunity to speak. I think I have the unenviable position of following that exciting talk from Matthias with something mundane like maybe it's not all dust. What I should say is tension is always creative, right? So it leads us to think about what the loopholes are in our theories, and even if the tension is resolved in ways like better scraping of the data or other aspects, it always creates new opportunities. So I don't want to say anything definitive here about, I'm certainly not going to say anything about dust in this talk, but there is this tension that we heard about this morning, and I'm going to entertain the possibility that we should take the data at face value, in which case, what are the ways to resolve this tension, and what are the directions they point us to in trying to confirm or falsify cosmological explanations of the tension we heard about. So I remind you that is, I should say that in this plot you already see it, that we've seen this before. That is that the excess that you expect from the addition of tensors at r of 0.2 is not observed in the Planck temperature maps. And could this have something to do with the other things that Planck has told us about cosmology, tension between the Planck data and the late universe data, that is, the local expansion rate and the local amount of structure, which also the Planck data has shifted to be in this range of interesting tension, that is 2 sigma-like tension, that is the creative spark that maybe we have a new idea of how to resolve this. And I should say people here have been much more creative than I have, so this is just set up for maybe some of the bolder ideas you'll hear about later in the conference about some of these issues. So I want to start with the bicep tension that we've already heard about, the tension between bicep 2 and Planck, or temperature and polarization, and to remind you that that's in the context of a power law, power spectrum, so inflation with slow roll, no features, and the lambda CDM cosmology, and the tension could be resolved in either way. And also the central to late tension, that is the Planck data, and what it infers for what we should see in the local universe, the expansion rate, the Hubble constant, and the amount of structure measured in the abundance of clusters of galaxies. And that could point us in the direction that maybe the cosmology is missing something in its energy density. So could things like dark energy explain it? Could things like neutrinos explain it? And to give you the bottom line, it's much like what we heard about dust. It's not conclusive right now, but there are directions where this points to in which there is a very clear prediction of what you should see if it's either of these explanations, and both of them involve getting better measurements of the EE polarization. I should say that this is work done with Cora Dvorkin, who is at the IAS, soon to be at Harvard, and Vinicius Miranda, my student at Chicago, both which Cora will be looking for faculty jobs. Vinicius will be graduating next year in case any of this work intrigues you. Okay, so let's start with the bicep tension with Planck. And again, like the speakers this morning, the first thing to say about this is just the incredible advance in sensitivity in this year alone, detecting lensing D modes, first in cross-correlation in SBT pole, and then polar bear, and then bicep in this bump that we're all trying to interpret. So what is the issue of the tension? The tension is that, as Mark told us long ago, there should be an effect in the temperature anisotropy. That is, gravitational waves come into the horizon, they decay, they give you an ISW effect. They should boost the temperature anisotropy. on scales that are above the horizon at recombination, because below the horizon, these waves have come in while the photon baryons were still very tightly coupled. Any quadrupole anisotropy that you generate that would give you an ISW effect is rapidly destroyed by scattering. So this is the sort of spectrum you would expect to see from a contribution from tensors. And the issue about the tension is that if you added this component, which is scaled to 0.2, you would exacerbate the well-known existing tension that has gotten worse in the Planck data that was already about 2 sigma. So in excess of the mild tension you had before having tensors in the spectrum, you've now exacerbated that, and now it's an over 3-ish sigma tension. And this is just the visualization of this. This is scaled now to R at the pivot point of 0.002. That's why you see the bicep 1 sigma errors are not centered around 0.2. And remember that SBT and ACT actually make this constraint stronger. So yes, there's a little bit of overlap, but this is the tension. And this is sort of a cartoon plot because I didn't plot you the distribution from bicep. OK, so that's the visualization. And it's the lack of this excess temperature versus the high level of tensors implied by the B-mode polarization without any foreground modeling, so just taking it at face value. So as you well know, that you could try to explain this by running the tilt. And what I just want to say here is that that really is introducing a feature in inflation. You can't get away with saying that this is a very large running of the tilt so that you suppress the amount of large scale power by running the tilt to have you have less power on long wavelength scales. Because that is too large for slow roll, which would be something where the correction would be the square of the difference between the tilt and 1. And really, if you wanted to use this sort of explanation, you're really talking about something that's transient, that is something that changes inflation, but only over a certain small number of e-folds. And if you wanted to really get rid of this excess power, which looked like almost a step at the scale of recombination, the horizon to recombination, you would want a sharper feature. So one, running of the tilt is a feature saying that the spectrum has a scale in the problem. That's the scale where it goes through a scale invariant spectrum. It's not scale invariant on either side. And 2, it would fit better if you had a stronger feature in the inflationary model. Okay? And you can see sort of the 2 ways out here. You could introduce a stronger feature, or you could try to change the cosmology, compromise, and make this the average spectrum to be closer to scale invariant across the scales where we're measuring the CMB. And that's the other way of solving it, to change the cosmological energy density content to allow now a scale invariant tilt. But for inflation, remember that that solution is not this m squared phi squared model, right? That's a solution where you have a scale invariant spectrum and a high tensor to scalar ratio. So either way, just m squared phi squared is in tension with the data without accounting for the foreground subtraction. So I want to use this as motivation. The tensions come and go, right? So we'll see in a few months how this resolves itself. But I want to use this opportunity to review a little bit about features and how you then think about this in sort of an inverse way. That is, what does the data want you to have to fit these sort of anomalies in the temperature data? And what do they predict you should see to make a claim about verification or falsification of a model like this? And not to give you anything definitive about whether this is the explanation or not, which we'll see in a few months. So remember that the idea is you have a deficit of power in the observed microwave background temperature field, which occurs on scales that are above the horizon during recombination. You have an exacerbation by trying to add tensors in. So of course, the first thing that you would say about what would fit the data is if you took the prediction for the scalar power spectrum and changed the tensor-scalar ratio in a step-like fashion, that of course would fit the data better, and that's obvious, and that I'll show you does fit the data better. What I want to emphasize here is that if you do that, you're going beyond the conventional slow roll approximation, where the slow roll parameters are both small and constant. So you can't just put a step in the power spectrum and analyze data and make predictions about what you should see about this. You have to go back and calculate the effect of putting in a step in the inflationary side of things in the slow roll inflationary parameters epsilon h, which is the deviation from your de Sitter expansion, and if you have a non-canonical kinetic term, the sound speed of inflation. They both go into the scalar tensor ratio. And the key is that the scalars are flexible. I'll show you the tensors are not, because the tensors really do measure the Hubble rate during inflation. And unless you have epsilon very large, you don't expect to perturb the tensors very much, and I'll quantify that for you. But you can do that to the scalars, so you can suppress the scalars, and it's not sufficient just to put features directly into the power spectrum. So what can you do? You can, of course, solve it directly model by model and propose a model like open inflation and calculate what you see in the spectrum. What I want to emphasize is there's this nice approach, which is called the generalized slow roll approximation, first introduced by Ewan Stewart over a decade ago, which is the tool that would be very useful to consider what the data want to see in the inflationary side, and then make predictions for what you should see in polarization and what you should see in tensors, although the tensor part will be very small. And the nice thing about this that may not be obvious is that you can make this very accurate. So I'll show you that really this is an iterative approach where you're assuming that what's small is not deviations from a power law in the power spectrum, but rather deviations that take you a little bit away from de Sitter. And you can iterate in this in a Green's function approach or a Born approximation-like approach. And what may not be so obvious to you is that the leading order, second order corrections come in as the product of first order transfers. So it becomes a linear problem that's accurate to second order, which makes it very useful for describing things that are order unity, almost order unity in the power spectrum language. And it is general for a wide class of single field inflation, including all of P of x and phi, which are non-canonical kinetic terms given by x, functions of x, or in the EFT language, anything that's described as the expansion of this Stuckelberg field, this G00 plus 1 operators. And it's also the same technique you would do for the bispectrum. So in principle, these models that would try to explain temperature anomalies also predict the non-Gaussianity. The non-Gaussianity is larger, but if you have something like what you want for bicep, where it's localized to a few e-folds, it's still not detectable. And I'll show you other models which are also trying to explain other anomalies in the temperature data that give you large bispectra which are detectable. So the focus is taking this and thinking about, from the data side, what the model side wants, and then predict what you should see to verify or falsify these explanations. And just for a heuristic idea of what I mean by this thing that controls the features in the scalar power spectrum really is just a generalization of the combination in canonical scalar fields, the combination that would give you the tilt. So we're looking at things that would make the tilt non-constant. Of course, it does more to the power spectrum than just do that, a running of the tilt. And this is just the way you should think about it. If you're thinking about a reconstruction of what the potential is telling you, it's the same combination that gives you the slope in slow roll inflation. And note that this is now going to be a large amplitude effect. So this is an order unity change in this measurement of the deviation from a power law, power spectrum. Okay, so let's apply this idea to bicep and see what it wants and what kind of predictions that would make. Whoops, something about the font came out wrong there. But that should say a delta chi-squared of 14. So as advertised, which is obvious from what you're adding in by the tensor spectrum, that what you would want in putting in a feature from the inflationary side is that you get a step in the scalar tensor to scalar ratio, which could either be change in slope of the potential, which makes a step in epsilon h, which maybe Leonardo will talk more about fundamental theories that give you that, or a step in the sound speed. And this is an example of both, which is if you put a step in the warp of a dBi model for inflation. And what you should see here is that it actually prefers to have even less power than R of 0. So because the lambda CDM spectrum already had too much power compared with the Planck data for the standard cosmological parameters that fit the rest of the data in the standard lambda CDM paradigm, what actually you would want to do to introduce a better fit to the data is actually even less power than R equals 0, which is why when you do all of these parameter estimations, it turns out to look quite a bit more significant than you would have guessed from that overlap plot of the tensor scalar ratio from Planck versus Planck plus SPT bicep versus, Planck plus SPT plus ACT versus bicep 2 in the polarization. That is, you could say it in the other way that Planck's limit on R was sort of artificially tight because they were already on a steep part of the likelihood function. It was already a bad fit to the data at the 2-ish sigma level. And now you've exacerbated. There's the 14. And I should say that if it goes down to R of 0.1, say it's half dust and half primordial gravity waves, because you were sitting on top of this existing problem, it's still a tension. That is, it's now down, instead of a delta chi-squared of 14, it's down to a delta chi-squared of 9. It prefers the same sort of net result, but with a lower addition of the red curve, the magenta curve, by a factor of a half. And what about doing this in the power spectrum directly versus having an inflationary model that does this? Two things that I want to focus on here. So this is the model run through and the predictions blown up, now not emphasizing the decrement of power that would explain this excess, but rather focusing in on what it's doing through the very well-measured regime of the first peak. So if you make a very, very sharp feature, and I'll explain why in a second, what you do is you don't produce a localized feature in the power spectrum. What you actually do is you produce a ringing of the power spectrum that goes all the way to high k, because what you're basically doing is putting a feature in the time domain and you're Fourier transforming that to the power spectrum. So if you have a sharp feature in the former space, you have ringing all the way out. And that's dangerous because the data is very, very precise through the acoustic peaks. So one thing is that you should do this sort of analysis through the inflationary model because it restricts what you could allow yourself to do. You can't put a step in the power spectrum. That would be not something that you could get from an inflationary side of things. And also, curiously, it actually fits the data better because having a slight ringing that you wouldn't get from just playing around with the power spectrum actually fits a known glitch in the first peak. So here's a blow up. Of course, it's not very significant, but it's actually helping you that you're going through this glitch area around L of 100 to 200. All right, and this is what it looks like, that model I've been plotting here as fitting the data very well. This is the source function, which you should think of as deviations from the de Sitter versions of your mode functions. And remember that in slow roll, this would just be tilt, and this would just be a constant. This is the sort of thing that would fit very well the spectrum of Planck. So the way this works in terms of thinking about this, not just solving a specific model and saying, Okay, this is the prediction of a model, but to think of this as a class of models and think about the class of predictions is that it is in the forward direction, a problem where these deviations from your de Sitter expansion then transfer onto the curvature power spectrum of the scalars and then transfer onto the observables, the microwave background temperature and polarization. And the key thing is that these are all linear transfers, even though I'm solving things to second order, so a nonlinear, formally nonlinear process. The leading order thing that determines these features in the power spectrum are just products of linear things, which means that I can do a linear transfer and think about inverting that. Okay, so how does this work in terms of why it causes oscillations? So this is the transfer function that takes some sort of feature in the inflationary space to the k-modes of the scalar curvature power spectrum. And what you should note is that smooth things would say that basically the tilt, this g prime function that quantifies my deviation, would be just freezing out at horizon crossing, in this case sound horizon crossing, because I've allowed for a sound speed of the inflaton. And that's the well-known ordinary slow roll approximation. But in more detail, the transfer function has these rapid oscillations. So if you now think about a localized feature in time or potential space, then it's picking out oscillations in k space. Think about putting a delta function source through this. It would ring like that. And that's exactly what you see in this example here. The ringing would continue until the finite width of whatever feature that I'm putting in. So this is, again, that step feature that fits bicep, and what it would predict from a deviation from this scale-free power law would be not just this decrement of power, but also a series of oscillations. And I have to be very careful not to overproduce this ringing, because that's something that is well determined by the data. So the next step of that is that the curvature power spectrum then gets projected into the temperature anisotropy and the polarization anisotropy. And the key thing is that a consistent explanation would produce features, definite features in the polarization field, the E-mode polarization field, given an explanation of what you see in the temperature modes. And again, those oscillations are beyond the slow roll approximation. So here's that transfer. Of course, it is a broad transfer given the various effects in the CMB transfer function, the acoustic peaks at high L, and the integrated Sachs-Wolf effect at low L. And the thing that you should see here is that the transfer in the E polarization, so you should read this as if you have a feature in K space of the curvature power spectrum, what you should see in the L space, correspondence in multiple space of temperature and polarization. The polarization E modes are much cleaner at determining features in the power spectrum. So it not only would be a matching feature, but it would be a more incisive matching feature if this sort of thing was explaining the data. So here's what you see for that one specific model. So in this case, what you're doing is you're suppressing the scalar power spectrum. So you have the tensor excess, because tensors produce E modes and B modes. So if I didn't have this scalar suppression, I would predict this magenta line. And I've, in the lower panel, given you the deviation from this power law model. And so what you should expect to see if this were the explanation is a suppression, again, matching the temperature anisotropy, but more significant in the polarization and more resolved in terms of the L space features of this. The oscillations, for example, are more resolved here than in the temperature predictions. Okay. I should also note that the regime here, where you might think you see big things that are soon detectable, are limited by reionization. That is, here I've just done a simple thing of fixing the optical depth during reionization and showing you the difference if I just change this scalar power spectrum. Of course, there are degeneracies where I could change the ionization history. The good news there, which I won't talk about here, is that there's enough information to separate the two if you had cosmic variance limited E-mode polarization measurements through this reionization pump. And even Planck can do a pretty good job of separating out what's from a change in the ionization history from a change in the primordial power spectra. The stuff above L of 30 is robust. So unless reionization is very, very different from what we expect, this should be a prediction of what you should see at L's greater than 30 in this specific model. So I have only given you one model, and I've shown you what it should produce. Okay, so what else does it predict as a specific model-to-model basis? Well, there should be matching things in the tensor spectrum itself. That is, you could do the same approach of taking your deviation from de Sitter, which is now suppressed because in this particular case, I haven't made epsilon h large, but there are other alternatives which actually have a fairly fast roll period, sort of seeing the beginning of inflation. And if you're willing to pump epsilon h up to the 10% level, then that would give you observable features in the enhancement of gravitational wave perturbations on at low k, at large angular scales. In this case, it's too small to observe, and the reasons are two, that it's suppressed by epsilon h, the generic prediction from the tensor-scalar ratio, that really you need a deviation, a large deviation from de Sitter expansion to produce changes from a scale invariant tensor power spectrum. And also, which may be less obvious, is that what produces very observable things in the scalar power spectrum is the sharpness of the way you can make transitions in the scalar power spectrum. And you can't do that for the tensors because, remember, you have to conserve energy. So even if you do something as sharp as possible, and I'll show you an example where you have a step in the power spectrum, a step in the potential of the inflaton, which you might think would give you a step in h, the Hubble rate during inflation. You can't, of course, do that because it conserves energy. So you're doomed to have features that are at least an E-fold wide by energy conservation, which means you can't produce very high K ringing in the tensor power spectrum, which may be a little less obvious from the slow roll standpoint. Okay, so there I've given you just an example. I've just said, okay, I've constructed a step model from inflation. I've tried to fit the bicep data. This is one model. It predicts one thing for the polarization. But now that you have this structure where it's all linear transfer functions that go from the inflationary side, a single function quantifying all of this slow roll, all of this single field inflationary freedom, to the observables, you can, of course, combine them all and think about this as a single linear transfer onto the observables and think about the inverse problem. So that is, I decompose this into a few steps here. I said, okay, propose a model for inflation, go through the scalar curvature power spectrum, predict your observables, temperature and polarization, E mode and B mode, and think about the forward problem. What you would like to do is the inverse problem. From the data itself, go from what the observables are and construct what your inflationary model that would match that is. So this is ongoing work, so I won't show you the Planck plus bicep results, but just the idea of the technique. In this case, we did it for the WMAP power spectrum, temperature power spectrum. And here we've done a principal components decomposition. So Cora Dworkin took the modes that are best observed from the WMAP data in terms of their deviations implied in the inflationary side, this G prime function that is the analog of tilt for this general case, and looked into whether there was significant indications of features from the WMAP data. And what pops out is the well-known feature that's the glitch at 20 to 40, which the 20 part is still in the Planck data. But you should see some similarity between this, which doesn't have tensors, by the way, so it's changed a little bit by the If you wanted to add in R of 0.2 for the tensors, this is just what the scalar spectrum would imply. And you should see some familiarity here of what that curve looked like versus that step example that I showed you fits now the bicep 2 plus Planck data. So when you do this, you can do more then, because you've got this inverse process. You've found everything through an MCMC that is consistent with a feature in the temperature power spectrum, and you can make predictions for what you should see in the polarization spectrum. Now, this is not Planck plus bicep, which is ongoing work with Vinicius Miranda, but this is what you would have seen to fit the glitch that still is there at L of 20-ish in the WMAP data. And here, the significant part of that is some prediction for what you should see in the corresponding range of the E-mode polarization field. So it predicts other things. So let's go through whether a model like that is actually acceptable for other reasons. It would predict a bispectrum because you have this feature during inflation. That means that you have these things generating interactions inside the horizon, which gives you nearly equilateral type non-Gaussianity. And so if you wanted to do that with those WMAP models that I showed you, you would predict a bispectrum that was large. This is FNL equilateral, essentially, on the y-axis and scale on the x-axis, which sounds largish. That is, you produce more than you would in slow roll single field inflation. But remember, it's localized to these few e-folds because this isn't a very sharp step. This is a fairly broad thing that would fit WMAP or Planck plus bicep. So the bottom line there is it's large non-Gaussianity, but only for a limited number of e-folds or range and scales, and this does not produce something that's observable in the Planck data. So let me transit a little away from bicep and tell you the more general features. That is, I want to emphasize what else you get out of thinking about it this way, and also other anomalies in the temperature power spectrum that are curiosities, I would say, less significant than this problem with a deficit of power. So here's what happens if you have a very sharp step. So remember that the observable is essentially going to be the Fourier transform of this sharp thing in time, which is going to ring in Fourier space. So the sharper you make it, the more you get oscillations that go out in the power spectrum in K space or in multiple L space. And this actually fits both starting with WMAP, where it was done for monodromy, looking for oscillations at high frequencies. This actually improves the fit to, and it was also done with Planck for monodromy, which made the significance a little lower, but something where you have a step-like feature similar to what you want for bicep, but now very much sharper and on slightly larger physical scales. You would produce ringing that goes all the way out, and it actually is favored at this delta chi-squared of over 10 in the Planck data. Now, I want to caution you, unlike the suppression of power that we're talking about in this bicep 2 context, this is something that oscillates really rapidly, multiple to multiple. In fact, it's about a delta L of 10, I think, actually 10 about in this case. So you have noise, you have cosmic variance noise, and you have instrument noise, which is also going up and down versus your ensemble average prediction. So you could easily get improvements like this just from fitting noise. So that's the cautionary thing. You shouldn't take this as an improvement that suggests that this has to be there. The nice thing is that if it is there, it produces a definitive ringing in the polarization field, which is either there or not. So this is very testable. The features are sharper in the polarization field, and it has to be a matching prediction. And that's one of the things that comes out about thinking about this as this process of linear transfer. And I want to emphasize just in this case, this that this is an example where even if you put the sharpest thing that you could, that was a step in the potential, it's still not sharp in the tensor sense. That is, the Hubble parameter during inflation by energy conservation says that that can only change on the expansion time scale. And even though the scalar power spectrum can ring all the way out in K, the tensor power spectrum cannot. You'll have these suppressed oscillations in the tensor power spectrum. But what does it predict beyond the polarization? This actually predicts large, observably large non-Gaussianity, basically because you're putting in this very, very sharp feature in physical space or temporal space, if you like. And any time where you have an endpoint correlation function that sits on this sphere of this radius in time or radius in physical space, you would get these enhancements of the correlations, which, if it were infinitely sharp, would have a mild logarithmic divergence. But of course, you have some finite width. So you would produce an equilateral bispectrum that rings all the way out. These tools of thinking about this in terms of an iterative process where you're looking for small deviations from the de Sitter expansion and iterating that through the equations gives you a very, very good approximation for what you see in the bispectrum as well. And Planck does not yet rule this out because it's a very, very highly oscillatory pattern for the equilateral bispectrum. But in principle, they could look for it if they put templates like this in. And in fact, the data don't put any limit on how big this is. It could go out to be a step function, no width to the thing. The Planck data and temperature would still say that's okay because they have a finite beam and they can't resolve all those oscillations. The limit actually comes from the theory side. That is, if you put in this sharp feature, you have a strong coupling scale and this perturbative expansion, this tree level calculation becomes invalid. And it's very similar to what people have worked out for slow roll inflation. If this is a hundredth of the horizon, this width that you're talking about, then everything is strongly coupled and it breaks down. So this would be allowed by the effective field theory, and it would be a large non-Gaussianity, and something that goes all the way out to 100 would be theoretically not possible. And that's what's actually limiting you. Okay, so let me think now if you found that unpalatable. So if you weighed is it dust versus is it features in inflation, and you came up with dust, what about changing other aspects to try to get compatibility between the observations? And this is sort of intriguing because there is this other tension between the Planck data set, the universe at recombination, and the local universe, the redshift 0 stuff. So let me address that and see where that leads me to. Does that lead me to a consistent picture about what could be explaining these things? Let me first put in a plug for local standards. So remember, the biased view from the microwave background is that we have very good measurements at recombination, and we're testing the consistency of our standard model, which now includes inflation, slow roll, and the standard components of matter and energy. And so if you wanted to do an end-to-end check of the last part, which is the contents of the universe in the late universe, what you would want to do if you were thinking about where you might expect the maximal deviations, or the end-to-end check of your cosmology, is to go to the lowest redshift. And the other advantage of the lowest redshift is that there are multiple ways of addressing these measurements. So there are consistency tests, because it's a very local measurement and has long been done. So it's good in those two senses. And these are things like the expansion rate and the amount of structure, which now I want to convince you. I don't think you probably need convincing, but the way this works is that the microwave background has calibrated under the assumption of what's going on during recombination in terms of the components of energy density, that we have photons, baryons, standard neutrinos, and cold dark matter, has calibrated a standard ruler, which is the distance sound can travel, to recombination. And in a flat lambda CDM, standard paradigm cosmology that we want to see whether there's any tension with, the only remaining freedom is the cosmological constant. And by Friedmann's equation, that's the only thing that is changing the expansion rate today from what you already know. So we know the physical energy density of matter because we measured it through calibrating the matter radiation ratio, and we're assuming that the radiation is the standard photons where we measure the temperature exquisitely well and we infer the neutrinos. That's how this prediction works, and in the flat lambda CDM model, there's nothing left. So the only thing that would vary H naught is the one missing thing in that statement, the cosmological constant, which means it's precisely predicted once you then go about and measure the angular scale in the sky, knowing this standard ruler, so that one thing is actually now your observable. Your observable is the distance to redshift of 1,000 measured from a standard ruler test. So that's all review. And just to remind you that why it's the Hubble constant that comes in, that is, the distance to recombination is just the integral over redshift of the inverse Hubble parameter. And with all the other energy densities defined, the only thing left is lambda. And when you measure d and z star through this angular diameter distance test, you infer what the Hubble constant should be. Now, the other nice thing about this test is that there are consistency checks on this that will become important for thinking about whether these things are actually pointing to new physics in some sector, like the low redshift side, the dark energy acceleration side, or the intermediate redshift side that we're missing something at recombination. And those two tests are with this assumption that we have all of the components of the universe at recombination being quantified by the cold dark matter, neutrinos, photons, and baryons. It predicts what you should see all the way through the spectrum. So in particular, it predicts this damping behavior in the microwave background, the random walk that a photon can execute by the time of recombination is a prediction. There's no other free parameters there, and the damping tail would have to match if that were true. And that's a test of our assumptions. And on the acceleration side, the test is the baryon acoustic oscillations are the same physics in the baryons, and they're measured very well. So if it was something that was on the low redshift expansion rate side, the dark energy, then we should see a change in the baryon acoustic oscillation measurements. Whereas if it were a change in recombination, we would see a joint shift in the microwave background and the baryon acoustic oscillations because we change how we interpret this scale. That is, we change the sound horizon instead of the distance. Just to quantify this for you a little bit, and the nice thing about this slide is I haven't changed it since Boomerang. This was the first time I wrote it down, I think, in Boomerang, so it's a very old slide. All I've done is changed for the incredible increase in precision through the intervening years from Boomerang to Planck. So basically, the thing that's important is how you calibrate this standard ruler, which is the distance sound can travel by recombination, which means that the thing that is mainly controlling your errors are the quantification of the matter radiation ratio, omega matter h squared. And the number for that, so if you look at these giant tables, one way to digest this table is to first stare at what happened to omega matter h squared, its central value, and its error bars. And that determines how well you can infer the distance to last scattering, because the angle is exquisitely precisely measured up to the point where things like lensing of the microwave background would make significant changes to that, but insignificant changes to the inference in cosmology, because you still don't know the calibration of that ruler as well as you do the actual measurement of the angle associated with all those acoustic peaks. So the bottom line rule of thumb is once you stare at how well the standard ruler is calibrated, you know how well the distance should be measured. That's about a quarter of the accuracy of the standard ruler calibration, or omega matter h squared specifically. And in the lambda CDM result, where you have no freedom between the two, that the matter radiation ratio tells you what the calibration of the standard ruler is, and the distance tells you what the remaining parameter is, the cosmological constant or the Hubble constant, the compensation you do to get the same angle on the sky in terms of how a change in the matter density affects what you infer for the Hubble constant is just that relation, that the fractional changes are the same. And more generally, if you allow freedom in the low redshift side, say change the equation of state of the dark energy W, or change whether you have curvature in the universe, or change the equation of state as it evolves, you can think about this compensation of what you would need to adjust to get in your observables the same angular scale of the acoustic peaks. And the further thing to note is that it predicts everything that you should see at low redshifts up to the point where we have the new physics, say, the dark energy. So that's that the distance to all redshifts in the deceleration epoch should also be predicted. So the baryon acoustic oscillations from the Lyman alpha forest, for example, which is in slight tension with the data too, but I won't try to explain that because that's difficult to see how to make it compatible. And also the amount of structure, which I will tell you about. So also the volumes are determined, and if you know the amplitude of structure from the microwave background, you predict what the amplitude of structure should be today in the context of all of those cosmological assumptions. So it's a standard model which makes falsifiable predictions, especially at low redshifts where deviations can be fairly large. So do we have any evidence for new physics? What do I mean by tension, and how big are the tensions? This is directly from the Planck paper, the comparison of now what you would infer from those arguments about the Hubble constant, the z equals 0 expansion rate from lambda CDM, flat lambda CDM, versus the actual measurements through the distance ladder. So to quantify that a little more, let me show you in the same way I showed you BICEP, the posterior distribution that you get from analyzing the Planck data versus the 1 sigma band of the measurements. On the left is what you infer for the Hubble constant, and on the right is a quantification of the amount of structure in the local universe. This is sigma 8 omega matter to about half, normalized in some fashion that is not important for this discussion. What is important for this discussion is the tension. So there are these tensions with our standard cosmological model, the flat lambda CDM cosmology, which are at the 2 to 3 sigma level, 2 sigma-ish for H naught and 3 sigma-ish if you take the extreme values of the cluster, X-ray cluster values for the amount of structure in the local universe. So intriguing, right? So what does this point to if you take it at face value? And I should say that in the intervening year, tensions can be resolved in different ways, including the march of people trying to look for systematics that might bring these to an agreement. I'm going to take it at face value. So you can look at what people say about recalibrating the masers and Georgia Stathiou's analyses. It's still, from the experts on H naught, hard to see how H naught would be less than 70. Is from recent stuff by Adam Rees. So there's a tension in the data, and what could explain it, and how do we go about verifying which of these explanations might resolve this tension? Okay, so let's start with the dark energy. If you wanted to keep this angular diameter distance, the angular scale of the acoustic peaks fixed by changing the equation of state, what would you do to try to get an inference and flat lambda CDM of 0.6 7-ish or 8-ish, up to the observed values that are more like above 0.7 to 0.74. Well, the way you would do that is that you would change the equation of state to phantom equations of state, which would be incredibly exciting. I would be almost excited about that as gravity waves. So if that were the explanation, that would be truly stunning. That would be not a cosmological constant and also an exotic equation of state that doesn't look like it would have an easy way to explain its stability. But what are the problems with that? What's the value of having this be a suite of consistency tests? So if I now look at what this predicts in redshift space, I can't just, of course, change the expansion rate today by energy conservation. I can't just arbitrarily change it at z of 0 and not have an effect at higher redshifts. So if I wanted to change the equation of state by this minus 0.2-ish level to bring a prediction of 67 all the way up to 74, this is what I would be predicting for the deviation in the expansion rate from the flat lambda CDM prediction at higher redshifts. Now, this sort of thing is very well measured now from the angular and radial scale of the baryon acoustic oscillations, and those are beautifully consistent with a flat lambda CDM prediction. So that is not a very good way to resolve the tension. It doesn't seem to be pointing to a change in the acceleration physics because the data points are very close to the lambda CDM prediction. And if you change the whole constant at redshift 0, you would change it all the way through the well-measured baryon acoustic oscillations. And it also does the opposite thing that you would want for the growth of structure. It enhances the growth of structure, and the clusters would like you to suppress the growth of structure. And it also is in tension with a supernova relative distance measures, looking at the relative luminosity distance between low redshift and high redshift supernovae. So it's good that we have this suite of tests, and it doesn't point in that direction. I could show you other explanations at low redshift, like the curvature. It also doesn't explain it. Now let's return now to the bicep story. That is, could we try to explain both things at once and introduce something that would not change the distances in the local universe, but instead change what we're calibrating through Planck as the inferences from the shapes of the acoustic peaks to the calibration of the standard ruler. Just to remind you, there's long been hints of things like this, so it's not outrageous to think that there are extra species of neutrinos from long-standing anomalies that haven't quite gone away, and in fact gotten more puzzling if I were honest about it, that hint that there might be extra sterile species of neutrinos that are partially populated in the early universe that would make contributions to the energy density at recombination. So the key for this purpose of thinking about whether it's a plausible explanation of these tensions is that it changes the expansion rate at recombination. It changes the distance sound can travel by recombination. That is, it changes the calibration of the standard ruler, not the inferences of distances in the local universe. So if you look at what it does in terms of thinking of this as a fully relativistic species that fixes the matter-radiation ratio through the shapes of the peaks, but adds radiation, also adding a compensated amount of matter to fix the matter-radiation ratio, and thinking about it as a massless, m goes to 0, extra species of neutrinos, a full thermal population, one extra thermally populated species of neutrinos would actually be what you want to make the Hubble parameter back up to it's closer to its observed value, and also keep all of the other tests the same, because now you've changed the calibration of the BAOs through the microwave background, and you haven't actually changed anything about the local universe. Before BICEP, this was a sort of compromise, and it's still a bit of a compromise, but more on the CMB versus the Planck versus BICEP side, But it was a compromise because that consistency test that I told you about was limiting you. So if you added an extra species of neutrinos, you change the distance that a photon random walks versus the sound horizon, the distance that the sound waves propagate, and you predict a different damping of the CMB. You predict extra damping, and the measurements by ACT and SBT placed limits on what you could do in the lambda CDM model. So what does BICEP do to this story? So BICEP would have an additional contribution to the temperature anisotropy on large angular scales, L corresponding to scales above the horizon during recombination, which you would like to suppress. And remember that first slide of the running of the tilt. What you would like is to make it more towards scale invariant if you wanted to get an explanation of this excess. And that actually allows more freedom on the high L side, right? So instead of having a very strong constraint from this lack of extra damping, now because I've relaxed the assumption on tensors, I can now tilt the spectrum back from a red tilt to a nearly scale invariant spectrum. Which means that if I now just look at the Planck data with an extra sterile species of neutrinos, or more formally in this plot, with that as a parameter, the effective number of relativistic species during recombination. And I'll tell you, this actually also has marginalized a mass for this extra species. Then you now, instead of having a very little overlap between the predictions of our cosmological model and the BICEP result for the scalar tensor ratio, now you have some significant overlap. It's still in the tails, so you haven't made this a perfect fit. So there's still some residual tension on the CMB temperature versus polarization side. But you've at least allowed, with introducing neutrinos, this extra freedom to tilt back the spectrum, suppress the low multiple temperature anisotropy, and simultaneously allow more neutrino species. So this is a possible way to relax the tension between these two observations. And the thing that has now no tension in it is the Hubble constant. So instead of something where the observed Hubble's constant was in the tails of this posterior distribution, you have something where, in fact, the central value is very close to the observed value for the Hubble constant. If you make this species massive at the EV scale that might have some bearing on these anomalies in the short baseline and reactor neutrino experiments, then you can also suppress through the free streaming scale of this neutrino the amount of local structure. And you can get some overlap between the predictions for the local amount of structure and the model with a massive sterile neutrino. Now, I should say that there is more residual tension here, so it is not a great fit to the data. It's still in the tails of this distribution, but those are only statistical errors for the cluster counts. And what I've drawn in the dashed line there is if you take their mass calibration, which, so the important thing is the experts here would know, is how you measure the mass of a cluster. If you said that you were underestimating the mass by 10%, which is in the allowed region for the mass measurements, then you're starting to get more significant overlap, but it is still some residual tension in the data. And this is just to show you some distributions. If you took this and worked out what you do when you do CMB predictions to think about the correlation between adding an extra species of neutrinos and the Hubble constant and versus the scalar tensor ratio. The Hubble constant that you measure in the local universe would give you central values of one extra sterile neutrino and compatible with an R of 0.2. And if you go through to the neutrino side of things, what you're implying is that something close to a thermally populated species of neutrinos as something like a half an EV would be the best compromise. For the inflation side, I should say that you have relaxed some of the tension, but you've made it in a way where you've gone back to a scale invariant spectrum. So if you're thinking about the NSR plane, what you've done is you've found a way from the cosmology to change the scalar tilt in a way that is not compatible with a positive exponent monomial inflation. In fact, you would need inverse power law if you wanted to get a model like that. So let me end there. Tensions are interesting. They point us to new directions. These are two sort of these are two ways of trying to relax the tension in the bicep 2 versus Planck data that give you predictable things, predictions in a way you would test whether these explanations are the right explanation or not. Maybe I'll skip to the end because I think I forgot to mention this. The SPT and ACT points for the temperature spectrum are actually limiting the amount in which you can add the extra sterile neutrino species. So if I didn't put that constraint in, I would allow more than one species. So the corollary to that statement is the improvement that we expect from getting the full E-mode power spectrum in terms of measuring that damping tail of the microwave background is the test of whether it's the neutrino explanation or not, just as the E-mode polarization in this bicep regime of L of 30 through 100 would be the test of whether it's an inflationary explanation. And remember that the two things differ in that you're changing the scalar power spectrum in two different ways, either introducing a sharp feature during inflation, which fits the data better, so it fits it better than a neutrino explanation, which is one that would tilt the power spectrum back to scale invariant and suppress the large angle spectrum relative to a red tilted spectrum. And I'll end there. Thank you. Good.
My earlier work, we have an arbitrary. Hello?
Could you elaborate a little bit on why you think that reconstructing the power spectrum using the E-mode is a lot more robust as compared to just using the temperature power spectrum?
Yeah. So first it's a prediction. So from an explanation of the temperature power spectrum, you can make a prediction for the polarization. In that regime of bicep, the cross correlation between T and E is fairly low, so it's an almost independent test. And the third thing to say is that the polarization in that regime is a very sharp transfer of power in the curvature power spectrum to the observable E modes. That is, the temperature power spectrum by projection is a broadened out distribution in L space for, say, a delta function in K space, whereas the E mode one is a lot tighter. So if you actually have a feature, it comes through better in the polarization E modes. Conversely, the B modes are very broadly transferred. So it's the E modes that are the test.
I actually had a second question as well. So when you look, when you're considering the transfer function both for temperature and polarization, what's your prescription for sampling the transfer function itself?
Yeah, well, this would go through the normal route of what you do is you introduce parameters on the inflationary side, and then you have all the machinery of CAM or your favorite Boltzmann solver do all those linear transfers for you. So you would incorporate the uncertainties and cosmological parameters that way.
More questions?
Okay, so I'm not a Big Bang nucleosynthesis expert, but as you introduce the N effective, the excess N effective, oh, yeah.
Yes, it changes BBM.
Yeah, go for it. Helium fraction.
Right.
Yeah.
So it would change the helium fraction. The helium fraction has been creeping up in some of the measurements. And if we get precise measurements, of course, this is also testable in helium and perhaps deuterium as well. But it's a matter of systematic errors. Right now, I think it is compatible, but it does change the helium fraction.
Okay, let's thank Wayne again.